Amy, the Chief Innovation Officer, CIO, for Stack Corporation, has a formidable task ahead of her, overseeing the rapid and seamless modernization efforts of the company's legacy application and services stack. We've covered her story in the day in the life of part 1 of this 2-part series. Brady, in our second part that we're working through today, needs to support the rapid delivery cadence of the CIO's department, ensuring agile but secure development practices across an ever-growing and more diverse team of programmers, IT administrators, and data scientists. In the closing modules of this hands-on material in part 2, we'll bring together the two personas from Amy to Brady and across the board. Amy and Brady will need to work together to deliver on Stack Corporation's vision of agile application development atop of an orchestration platform like OpenShift that has been hardened for the security needs of enterprise. As new parts of the business are brought on board and new users are added to the environment, Brady's team must continuously evolve their rubric for how access to protected Linux functions are granted across an ever-increasingly complex series of applications, services, and deployment requests. How you go about securing a container and the approaches that you take to achieve this depends on the background of the person that you're asking. For example, if your background is in managing infrastructure, you might perceive a container as a lightweight alternative to virtual machines. And in that way, think of it as a sandboxed application process that shares a Linux operating system kernel with other containers. Alternatively, if your background is more of a developer pedigree or a programmer, you might be thinking how to conceptualize a container as a packaged bundle of application code and all of its dependencies able to be provisioned within seconds and deployable inside of essentially any environment that you need to or of your choosing, readily enabled for continuous integration and continuous delivery using CI/CD. Regardless of whether you subscribe to the application builder or infrastructure manager perspective on containers in general, there are 7 key elements that are essential to securing any containerized system. These 7 elements encompass each layer of the container solution stack, like you would do for any application stack or any running process, and from the time that you deploy your application and the container all the way throughout the life cycle of that containerized application to when it's placed in production. So let's tackle each of the 7 best practices for how you can secure containerized environments across an orchestrated multi-cloud environment. The first is multi-tenancy and the unusual world of container host operating systems. We mentioned before how containers simplify work for developers by allowing containerized applications to be conceptualized as a single bundle of your code and all of its dependencies as a single unit. This has the knockdown effect of having multiple containerized applications that are able to run on a shared host, as all containers can be deployed into a multi-tenant fashion on the same machine without cluttering or polluting the underlying operating system with all the conflicting binaries, libraries, and dependencies that those apps might need to run. With containers, you also eliminate the need for traditional VM hypervisors or guest OSs, further decreasing the complexity and the size footprint that would otherwise be placed on hardware with a virtual machine alternative. The linchpin therefore becomes the OS these containerized applications share and run upon. Decreasing risk to the shared OS begins with how you design your containerized applications to begin with. For example, you should drop privileges from the application where you can and assign only what you need to require at a minimum to create the containers with the least number of OS level permissions possible. Security aficionados tend to group this concept into something that they call principle of least privilege, a cornerstone of any security playbook. Run and execute applications such as user rather than root wherever possible, and that's something that we've been practicing in our lab work thus far. The second task is ensuring that your Linux operating system is surrounded by multiple levels and layers of security. Red Hat CoreOS and Red Hat OpenShift are positioned to secure the Red Hat Linux operating system CoreOS through a combination of SE Linux, which is available as part of OS and as part of RHEL, for isolation of namespaces, control groups, or C groups, and more. Namespaces provide a level of abstraction inside of a container to make an application appear as though it is running its own OS inside the container with its own dedicated allocation of resources from the global pool. SE Linux isolates containers from the host kernel as well as containers from each other. Administrators can enforce mandatory access controls or MAC controls for every user, application, process, or file. Compromised containers running on the same host OS is a common vector of attack for those looking to exploit unsecured networking between containers not running on SE Linux. Utilizing C groups can place limitations on the resources that a container or a collection of containers is able to consume from the host system, mitigating their ability to stomp over or run over other healthy containers. The second key point is trusting your sources. You must be mindful of any packages or external code that you bring into your environment. Can you really guarantee that the container you've downloaded from a third-party repository won't compromise your infrastructure or contaminate other containers running in the same environment? Does the application layer of the container have vulnerabilities that could be potentially exploited in future? What is the frequency with which the container is updated by those external parties, and who ultimately are the author of those updates? Containerized software from a public repository, even ones hosted on a highly reputable distributor like a Docker Hub or a GitHub, carry the same potential risks. The unavoidable fact is that if your organization is working from containers published in those public repositories, you are ultimately inheriting code and work performed by others and not in-house. And those individuals may be ones that you're not familiar with or have never met. This is not to suggest that code from public repositories is riddled with malicious code, far from it, but there is always the risk that containerized code may inherently or inadvertently come with vulnerabilities that the original developers failed to recognize, and it's up to you to then secure later on. Modern software projects are enormous undertakings and might contain upwards of thousands of different dependencies and libraries. If you're working with someone else's code or another person's container, some of those dependencies won't be fully under your own control. The reliance that we as developers or programmers have on extending the open source projects of others and the need to include dependencies within our own projects over which, again, we have very limited or no control. One way to mitigate the risks is to work with trusted and established vendors when sourcing containerized application code. For example, Red Hat has been packaging and delivering trusted Linux content for years using RHEL. And likewise, they do the same now via Red Hat certified containers that can be run anywhere RHEL or CoOS runs, including OpenShift. Red Hat Quay Container and Application Registry can also provide additional levels of security storage, distribution, and deployment of containers on any infrastructure for those who might need it and want a little bit more assurances in terms of the vetting that goes into where their containerized code is coming from. If you want to use your own container scanning tools to check for vulnerabilities or other exploits, you can also use RHEL's and OpenShift's pluggable API to do so. The third step is protecting the software build process. For containers, the build phase of an application's lifecycle occurs when application code is integrated with runtime libraries and other dependencies. One of the key hallmarks of containers is the repeatable, consistent manner with which they deploy across any infrastructure. Consider the frictionless portability of these containers and the multitude of environments or clusters that one container might be deployed into over the course of its whole lifetime. Defining what and how a container is deployed, the build process, if you will, is critical to securing a container that may be deployed dozens or even hundreds of times across its lifetime and its history. The source-to-image, or S2I, open source framework that was covered extensively in part 1 of this lab work provides build management and image security for containerized applications and code. As developer code is built and committed to a repository like Git, a platform like OpenShift can trigger CI/CD processes like we saw in part 1 to automatically assemble new container images using the freshly committed code that was pushed into those Git repositories. Deploy that image for testing, and then promote that tested image to full production status within your OpenShift cluster. Ultimately, this approach of securing the software build process allows operations teams and Brady's team of the CSO office to manage your base images, architects to manage software needed by those application layers, and developers, enabling them to focus on writing better code and worrying less about security. The fourth item is wrangling deployments on your clusters. Tools for automated policy-based deployments can further secure your containers beyond the software build process and into the production deployment phase. The fifth item is orchestrating securely. So modern microservices-based applications are of course made possible in part because of the orchestration services that Kubernetes provides, which handles complexities of deploying multiple container applications across distributed hosts or nodes. However, as is the case with any large open source project that we've ever been involved with or that you'll likely ever work with, the rolling of your own version of Kubernetes is often harder to implement from scratch and is often more rife with challenges than doing so from a packaged enterprise solution. So ultimately, the question is, why do it yourself when you can adopt an enterprise hardened Kubernetes orchestration platform already, one that's been engineered with the security principles at the core and at the kernel of everything that they do? One of the key tenets of any successful orchestration platform should be access to collaborative multi-tenancy between all members of a client's workforce while ensuring that the self-service access that they have to that environment remains secure. Ultimately, that's what we're trying to do here today between Amy and Brady. When you think about it, selecting a container orchestration platform on top of which you'll run your data, your services, your applications, and your users is akin to determining the center of critical mass for your modern IT estate. It is the center of gravity, if you will, for your hybrid multi-cloud architecture, and this platform will serve as the nexus of all future investments that your business makes towards that hybrid multi-cloud environment, the hub for both your workforce and your customer base, and naturally where data will begin to accumulate from those sources and where it will reside in the long term. Selection of an orchestration platform with enterprise certified security for containerized workloads ahead of time and already built into the Kubernetes layer puts your organization in the best position moving forward. The sixth item is around network isolation and API endpoint security. When working with containerized applications that are deployed across multiple distributed hosts or nodes, it becomes critical to secure your network topology. And essentially what that means is your network namespaces that usually assign port ranges, IP addresses, and so on to the collections of containers and applications running in those containers, which helps to distinguish them from one another. This is helpful for isolating things like dev, test, and pod environments within the same infrastructure. A container orchestration platform that uses software-defined networking, or SDN, to provide a unified cluster networking approach to assigning namespaces, or pods, can simplify this architecture immensely. A platform that is able to control egress traffic, outbound data moving outside of the cluster using a router or firewall method, will allow you to access and conduct IP whitelisting, explicitly stating which IP addresses are allowed or denied access to the cluster from others, and for further access control to the network. Red Hat OpenShift supplies all these tools that are well known in any best security practices playbook, as well as numerous other networking security measures in abundance. The final and seventh topic is federation of containerized applications. Federation is invaluable when deploying and accessing applications that are running across multiple distributed data centers of clouds. Kubernetes orchestration supports and facilitates this in two different ways. Federated secrets automatically create and manage all authentication and authorization secrets, or sensitive information like API keys that serve as license files, passwords that get buried in configuration files, and so on. And that's done across all clusters belonging to the federation. The result is a globally consistent and up-to-date record of authentication secrets across the whole of the cluster. Federated namespaces create namespaces in the federation control plane, ensuring that Kubernetes pods have consistent IP addresses and port ranges assigned to them across all the federated environments that are assigned and belong to that OpenShift cluster.